for the second example, range of the function is equal to 1, 2 and 5, and codomain is equal to 1, 2, 3, 4, 5. So range of f is subset of B, that is okay, but range of f is not equal to codomain. Okay, so here range of f is not equal to codomain, so that is not onto function. Well, for the first one, here the range of the function is 1, 2, 3, 4 and codomain is also 1, 2, 3, 4. So range of f is equal to codomain, so that is onto function, right? Now if we discuss about the 1, 1 and onto both, are the following functions onto 1 to 1 both or neither? Because that is very important for the inverse of any function. If we want to give the definition of when we can find the inverse of any function, then the answer is if the function is 1, 1 and onto both, then we can find the inverse of that function. So first we will look which functions are 1, 1 and onto both. So if we look at the PPT, then here this function is 1 to 1 because A with 3, B with 4 and C with 1. But this is 1 to 1 function, but this is not onto because 2 is not relates with any element of the domain. So this is not onto function. Okay, the second one is onto but not 1, 1 because here range of the function is 1, 2, 3 and codomain is also equal to 1, 2, 3. So this is onto function, but this is not 1 to 1 because here in codomain 2 is the element which is relates with two elements of set with the domain A and D. So this is many one function, not 1, 1 function. So this is the example which is onto function but not 1, 1. This is the third example. This is 1 to 1 and onto. We can easily see that this is one element with one element, and range of f is equal to codomain. Okay, so this is both 1 to 1 and onto. This is not 1, 1 as well as onto. This is neither 1, 1 nor onto because this is here 2 is also here again 2 is relates with A and C, so that is not 1, 1, and the element 4 is not related with any element of the domain. So this is neither 1, 1 nor onto. This is not a function. Okay, this is not a function. Not that here the element A of domain is related with two elements of set B, that means codomain, and as per the definition each element of set A should be related with unique element of set B. Here A is related with 2 and 4 both, so this is not following the definition of function, so this is not a valid function. Okay, consider a function that is both 1, 1 and onto, that is called bijections. Here this function is bijection because that is 1, 1 and onto. Now if we discuss about the inverse of the function, here let the function fx is equal to 2x, then this function f is from R to R, fx is equal to 2x, then f inverse is equal to the domain of the f will becomes codomain and codomains becomes domain. Here domain and codomain both are R, so f inverse is also from R to R, and f inverse x is equal to x by 2 because in fx x is multiplied by 2, so in f inverse x, x is divided by 2 because this is the totally inverse procedure. Okay, so f of 4.3 is equal to 8 by 6. So in f inverse 8.6 is equal to 4 by 3. Okay, this is the about the inverse of the function. If we discuss more on the inverse function, can we define the inverse of the following functions? What is f inverse of 2? Because we cannot define the inverse function here because this is not onto function, right? So if the function is 1 1 and onto, only then we can define the inverse of that function. Here we cannot define the inverse of this function because this is not onto function, so we cannot find f inverse 2. Okay, so that is not onto. That is, here the function is onto, but that is not 1 1. So here also we cannot find f inverse 2 because this is not 1 1 function. So we can conclude that an inverse function can only be defined on the bijection. That means we can define the inverse function only when the function is 1 1 and onto both. This is the idea of the composition of the function f over g x. Then f over gx is equal to f of g of x. If f of x is equal to 2x plus 3 and g of x is equal to 3x plus 2, then g of 1 is equal to 5 and f of 5 is equal to clearly 13. So we can say that f over g1 is equal to f of g of 1. That means g of 1 is equal to 5, so f of 5, and f of 5 is equal to 13. So answer of f over g over 1 is equal to 13. This is the one small example of composition of function. The idea of composition is like this one. This is the function g from a to b. This is the function f from b to c. The answer of first function from a to b comes in the b, and b is the domain of the function f. So that will directly put into the set c, which is the codomain of f. So first one is from a to b, which is g, and second is from b to c. Here a, if we apply g over a, so g over a comes in the set b, and set b is the domain of f, so we can apply function f on g of a, so that we get f of g of a in the set c. Okay, so we can say that if we apply f over g on an element a, we will get answer in set c, which is f of g of a. Okay, and the function g is from a to b, f is from b to c, but f over g is from a to c, as we can see in this figure. Okay, so this is about the composition. Here what we have discussed, the example. Okay, so 1 f of 1 is equal g of 1 is equal to 5 in the set R, and g of 1 is equal to 5 is set R, and if we apply f on 5, then f of 5 is equal to 13, which is in set R in the codomain of f. So f over g on 1 is equal to 13 from R to R. Okay, so this is all about the composition of functions. F over g of x is equal to, first g of x is equal to 3x plus 2, and then we apply f, then 2 into 3x plus 2 plus 3 is equal to 6x plus 7. Now the question is, f over g x is equal to g over fx or not? So answer is very clear cut here. If we take fx is equal to 2x plus 3 and gx is equal to 3x plus 2, then f over gx is equal to f of g of x is equal to 6x plus 7, as we discussed. But g of f of x is equal to 6x plus 11. Both are not equal. So f over g is not equal to g over f. That means function's composition is not commutative. That means f over g is not equal to g over f. They are different. Now let us look at more useful example as per the exam point of view. Normally in G2 exam there are some kind of example, basically depends on the definition asked normally in the exams. So let us look at some example which are frequently asked in the G2 exam. So we will try to solve it practically. Okay, let us look at the first example. The question is, if f of x is equal to 1 minus x upon 1 plus x, then prove that f of x plus f of 1 upon x is equal to 0. This example was asked in the exam July 2010. Okay, in the July 2010. So this kind of example are very easy to prove, because here we have given f of x is equal to 1 minus x upon 1 plus x. So here if we want to find f of 1 upon x, then we will put 1 upon x instead of x. So we will get 1 minus 1 upon x upon 1 plus 1 upon x. So we will get it's equal to x minus 1 upon x upon, that means in multiply, x upon x plus 1. X cancels, so we will get this is equal to x minus 1 upon x plus 1, which is f of 1 upon x. If we put the minus sign outside, so we will get minus of 1 minus x upon 1 plus x. So here we will get f of 1 upon x is equal to minus of 1 minus x upon 1 plus x, and here we want to prove that f of x plus f of 1 upon x is equal to 0. So we have now f of x is equal to this one, and f of 1 upon x is equal to this one. We have get. Okay, so if we take the left hand side, so we will get fx plus f of 1 upon x, fx plus f of 1 upon x is equal to fx is equal to 1 minus x upon 1 plus x, and f of 1 upon x we get minus of 1 minus x upon 1 plus x, and which is directly equals to 0, which is our right hand side, and this is our left hand side. Okay, that is our left hand side. So we have solved this example that f of x plus f of 1 upon x is equal to 0. So this example was asked in July 2010. If we look at one more example related to function, then let us look at the second example. The question is, if f of x is equal to log x, then prove that the first one is f of xy is equal to f of x plus f of y, and second one is f of x upon y is equal to f of x minus f of y. This example was asked in January 2012. Okay, so here before we solve this example, we have to remind, we know that log a into b is equal to log a plus log b, and log a upon b is equal to log a minus log b. So before we solve this example, we have to use that formula, because here we have given that f of x is equal to log x, and we need to find f of xy and f of x upon y, and we need to prove that f of xy is equal to f of x plus f of y, and f of x upon y is equal to f of x minus f of y. Okay, so here for the first one, f of xy is equal to f of x is equal to log x, so f of xy is equal to log xy, right? So as per our logarithms formula, log x y is equal to log x plus log y, and log x is equal to f of x and log y is equal to f of y. So this is our left hand side and this is our right hand side. Okay, so this is the first one, and in the same way for the second one, if we let f of x upon y, f of x is equal to log x, so f of x upon y is equal to log x upon y, which is equal to log x minus log y, which is equal to f of x minus f of y. This is our right hand side. So this kind of example are frequently asked in the GTU exams from the function side. Okay, so that's it for the function. Now we are quickly moving to our next topic, which is limit. Today we will start with the definition and the idea of the limit, and then we will discuss some basic examples on the limit. Okay, so in the limit part, what is the idea of the limit? If we look at this function fx is equal to x cube minus 4x square plus x plus 6 upon x minus 2, if anyone asks that what is the